So students, welcome to this lecture number 4 on the chemical equilibrium. In this lecture, we are going to discuss the equilibrium constant for the homogeneous equilibrium. So let us write that today's heading of this lecture is equilibrium constant This is KK Mukherjee in the Science with Mukherjee Sir YouTube channel. What is homogeneous equilibrium? Homogeneous means the system, homogeneous system means that when the reactant and the product will be in the same phase. As for example, this is the reaction, gaseous reaction of hydrogen in this reaction. You can easily observe that here the reactant hydrogen and nitrogen is in the gaseous state, right, in the gaseous state, and its product ammonia is also in the gaseous state. So this reaction, both the reactant and product are in the gaseous state, and the equilibrium achieved for those reactions we will call it is a homogeneous equilibrium. So we can understand what is homogeneous equilibrium. Homogeneous equilibrium is basically when the reactant and product will be in the same phase. Homogeneous reactions. So this is homogeneous equilibrium. Another example of the homogeneous equilibrium I am giving, that is the hydrolysis of ethyl acetate, C2H5. It is in the aqueous state. Then aqueous medium we have required for this reaction, and it will going to produce two product, that is acetic acid in the aqueous medium plus C2H5OH into aqueous medium. So this is also, you can see the reactant is in the solution phase. This in the solution phase, and the product is also in the solution phase. This is product and this is reactant. So this also a example of the homogeneous reaction or a homogeneous system, and the equilibrium in this system we will call it the homogeneous equilibrium. Now we want to make a equilibrium constant for the homogeneous gaseous reactions. Equilibrium constant. Already we know what is equilibrium constant. In the previous lecture we have discussed in detail. This is basically the ratio of the product, concentration of the product and the concentration of the reactant, and we have to consider the stoichiometric coefficient of the reactions, balanced reaction. So far we have expressed the equilibrium expression in terms of the molar concentration, and it has been represented as Kc. Kc is in terms of the molar concentration, right? Molar concentration. Molar concentration means the concentration is expressed in terms of how many moles present of the reactant and the product. This is molar concentration, and molar concentration. And now for the gaseous reaction we can also express the equilibrium expression, equilibrium constant in terms of the molar concentration, but for the gaseous reaction, it will be much more convenient that to use the partial pressure of the gas during the reaction after the equilibrium, when the equilibrium has been reached, and we will consider the equilibrium constant for the gas having the different partial pressure, and this partial pressure we will consider the equilibrium constant, and this is called Kp when we express the equilibrium constant in terms of the partial pressure. So two type of equilibrium constant we now understand. One that is in the molar concentration and other in case of the partial pressure. In this video we are going to discuss what is the relationship between these two equilibrium constant, right? Taking the example of the gaseous reactions. Okay. First, the reactant and product ideal gas equation. So here what is the notation that we know? This is a pressure, this is the volume, this is the mole, this is the constant. So we can write here also, this is pressure, pressure of the gas, pressure of the gas. Okay. Now this is volume, volume, and this is the number of moles, number of moles, and this is universal gas constant, universal gas constant, and T is the temperature in Kelvin scale, temperature in Kelvin scale. Now this equation can be written like this way: P pressure is equal to N by V into RT. What is N by V? N by V, N by V is the concentration term, and it will be the molar concentration. Molar concentration, when we are taking N equal to mole, then it will be the molar concentration. Suppose this molar concentration is equal to C. So we can write this P equal to CRT. Right? So we can write here one of the very vital thing, that pressure is directly proportional. We can write this pressure of the gas, pressure of the gas is directly proportional pressure of the gas is directly proportional to concentration. Concentration, right? So we can easily write this pressure of the gas directly proportional to the concentration. So by this you can have Kc. Suppose we are taking a equation that is H2 is equal to I2 for this equation. Kc, that will be concentration of HI, the whole square, divided by concentration of hydrogen and concentration of iodine. This is the Kc. Now in the similar fashion we can also write as Kp also. Kp is written like this. Kp is partial pressure of Hi, the whole square, divided by partial pressure of H2 into partial pressure of I2. This is the equilibrium expression for the Kp, and this is the equilibrium expression for the Kc. The difference is here, that is we are taking the concentration term at the equilibrium point, and here we are taking the partial pressure of the gases in the equilibrium point, and this is a balanced chemical reaction, balanced chemical equation. So now we understand what is this. Now we want to relate these two terms, Kp and Kc. How do we relate? That we will now discuss. Now we know Kp for this reaction. We are taking this reaction, that is H2 plus I2 is 2HI. This reaction we are taking, and for this reaction Kp will be given by this expression, that is HI to Kp is partial pressure of this hydrogen iodine square, partial pressure of H2 and partial pressure of I2. We know already we know that partial pressure of the gas is directly proportional to its concentration. So we can write the partial pressure of HI is equal to the concentration. Concentration is given by this square bracket, this concentration, and it is R into T. Similar fashion, the partial pressure of hydrogen, that concentration of hydrogen into RT, and the iodine, for the iodine gas it will be the concentration, molar concentration of iodine into RT. What we will do? We will put this value here. So it will, suppose we are putting this value here. So what we get? Now we get, that is HI RT its square divided by HI divided by, that is we put the partial pressure of hydrogen gas, it is given here, the concentration of hydrogen into RT into the concentration of iodine into RT. Okay, so what we get? We get this RT square will be cancelled out, so we get HI square divided by concentration of iodine, concentration of this. So we get this is a Kc. So for this equation we derive a thing as Kp is equal to Kc. But this will not be case for all the reactions. Suppose we take this reaction, N2 plus 3H2, and it will give 2NH3. For this Kp will be, if we take this HI, concentration of NH3 into RT square, then we get the concentration of the N2 into RT and the concentration of H2 the whole square into whole cube into R3. So what we get here from this, Kc will be RT minus. So here you can see Kp is not equal to Kc, rather Kp is less than Kc. So we will take a general equations, and for this we will understand it. This is a general equation, and for this general equation we can have this Kp is equal to, we can have the concentration of the product C at its stoichiometric coefficient small c into RT to the power C. Then concentration of D and RT per small d. So we can simplify this equation, that is Kc, or we can get another step, that is C so we can get this here RT C plus D with that it is, we can write the Kc is equal to RT C plus D minus A plus B. So we can write either further Kc is equal to RT to the power del N, where N is A is given by this, that is number of moles in the product minus number of moles in the reactant in the balanced chemical equation. In the balanced chemical equation. So this is the done. Suppose del n is equal to 0. Then we can say Kp is equal to Kc. If del n is equal to greater than 1, right, then Kp will be greater than Kc. Del n is less than 1, then Kp will be less than Kc. So this is the things that we understand. Three cases normally arise. As for example, HN, H2 plus I2, we have found this Kp is equal to Kc. For this ammonia and hydrogen, we will find that Kp is less than Kc. And for the other reactions, we will find this also. Okay, I think this is well understood. And now we do some numericals that will give you which type of numericals that may come in your examination, and that will help you to understand this concept very well. Okay, this is the numerical you have given for the reaction N2 gas plus O2 gas. It will produce the NO. It is a reversible balanced equation, and the value of Kc at 0.1 at 100 degree Celsius, because the equilibrium constant will be dependent on the temperature. If temperature change, then equilibrium constant will change. So the temperature has been mentioned here, where the concentration of both the reactant is 0.5 at the equilibrium point. When the reaction has reached to the equilibrium, at that point the concentration is 0.5 milliliter mole. Concentration is mole per liter, 0.5 mole per liter, and the Kc is 0.1. Then you have to write, you have to see which will be the value of the Kp. The option is given here. For that, what we will do, we have to remember this relation, that is Kp is equal to Kc RT into del N. RT into del N. So what we have to do? We have to, you know this Kc, and you have to find out this del N from this equation. And from this equation you can understand del N is equal to, because reactant mole of the reaction is 2 and mole of the product is 2 and mole of the reactant is 1 plus 1 that is 2, that is will be 0. So you can see Kc into Kc is 0.1 is given, right, and RT to the power 0 means RT is equal to 0, so it will be 0, 1. That Kp is basically the 0.1. This is the right answer. So this equation, this relationship is very important. Lot of numericals will come and you have to apply this. Second question, if Kp for a reaction, this is a reaction is giving here, is 0.05 atmosphere at 1000 Kelvin and its Kc in terms of R will be this, all this option is given. So you have to see which option is correct one. This can be easily been solved from this. Kp is equal to, we know, R T to the power N. Okay. Kp is given here. What is 0.05? 0.05 atmosphere. Kc, we have to express this Kc in terms of R. So R will be kept as it is. T is given here 1000. And now we have to calculate the del N. What is del N here? This is the product 4 and this is your this. So del N is equal to 1. So this will be 2 to the power 1. So Kc is equal to 0.05 by R into 1000. So it will be coming around 5 into 10 to the power minus 5 by R. And this will be the answer. Okay. So in this way, a lot of questions will come and you have to remember this very important relationship between the Kp and Kc. Okay. That is all for today's video. In the next video, we will discuss about the heterogeneous equilibrium, because this is homogeneous equilibrium. And then next video we will discuss the heterogeneous equilibrium. And thank you very much for watching. If you like this video, you can share to your friends. Thank you very much for watching. Thank you.